So, hello everybody. Today again, we are discussing lecture number 11 in the series of fluid mechanics. So, in this lecture, we are having three agendas over which we are going to discuss. Okay, the first agenda is no slip condition, and the second one is no temperature jump condition. Okay, so both of these conditions are somewhat similar, or maybe the conceptual wise, they are both are same. Okay, so we will discuss it. So, let's suppose I am starting with an example. Okay, so we are taking a case of pipe flow. Okay, so I mean, okay, let it be, it doesn't matter. Okay, to us. Okay, it's okay. Now a pipe is there, right? And this brown line is the pipe ball. Okay, that means this part. Okay, we will write it later. These brown lines are solid, right? I mean the pipe ball, either made it of metal or the concrete, or anything. Okay, that doesn't matter to us. Just we will take it as a solid. Okay, this is not fluid. Okay, okay. So now a fluid is flowing over there. Okay, come on, yeah, fluid is flowing there. Okay, and now see. That means in the upward boundary there is solid, right? And this the inside of this cylinder there is, oh, white, yeah, not working. Okay, so these things are liquid, right? And the above things are, I mean, liquid or the gases. I mean, we will collectively call it as a fluid. That doesn't matter whether it is liquid or the solid. We will discuss it later how this condition varies for liquid and gases. But for now, we just take it inside of the cylinder. A fluid is flowing, and on the boundary solid is there, right? So when a when a fluid is bonded by a solid surface, molecular interactions causes the fluid in contact with the surface to seek momentum and energy equilibrium with that surface. Okay, so I've told you this statement. So what this statement means, ki, let's suppose at the interface, let's suppose this is the interface, right? So this one is the solid particles. Okay, this is the fluid particles. So I mean, during the molecular interaction, means whenever this fluid particle interacts with the solid particles, they interact to cause a equilibrium, right? They interact and then wanted to be in equilibrium condition. Okay, so for making this in equilibrium, these fluid particles try to, I mean, this boundary particles only, I'm talking about these particles. Okay, only the particles at the interface. Okay, so the particles at the interface, they tends to take the momentum and the energy of these solid particles. I mean, I want to say ki momentum of fluid, okay, is equal to momentum of solid. Okay, as well, energy of fluid is also equal to energy of fluid. Okay, I mean, fluid is equal to solid. Okay, so in both these conditions to satisfy, then we can say that the molecular interaction, I mean, tends to equilibrium. Okay, so for equilibrium, tending to equilibrium, these two conditions has to satisfy. I mean, the momentum of the fluid is almost same as momentum of the solid, and the energy is also same as to solid. Okay, so momentum in equilibrium and energy equilibrium both has to be satisfied, so that we can say that after molecular interaction both are tending towards equilibrium. Okay, so all liquids essentially are in equilibrium with the surface they contact. Okay, so I mean, all the liquids or all the gases, for gases there is exception. I mean, when gases are most rarefied, I mean very thin, I mean the density of the molecules is very thin, I mean very low. In that case, these conditions may exceed. Okay, I mean excelled, that this equilibrium condition may not satisfy. Okay, so for now we are excluding these rarefied gases, I mean very thin gases. So if we exclude those conditions, then from these two condition we will make equation such that the fluid I mean velocity of the fluid, okay, is equal to velocity of the solid. Okay, And for energy we will say that, for a fluid, the energy can be expressed in terms of temperature. So we can say that the temperature of the fluid is also equal to the temperature of the solid. Okay. And for what cases we are saying this? We are saying at the interface only, right? At the interface only. At the interface only. Okay. So if we are talking about only with the liquid which are at this this just adjacent to the solid, then these conditions would satisfy. Okay. So this one, the first, in this equation, volume velocity of the fluid is equal to velocity of the solid. This is known as no slip condition. Okay. I mean no slip condition. From the word itself we can say that the fluid is not slipping over solid. Okay. It's just getting attached with the solid. Okay. And temperature of fluid is equal to temperature of solid. This one is known as no temperature jump condition. Okay. No temperature jump condition. Okay. The temperature at the solid and in the interface, the temperature of the solid and the temperature of the fluid should be equal. There is no temperature jump in the fluid. Okay. So these two collectively known as boundary condition, or we will use it as a boundary condition. Okay. So what do you mean by boundary condition is, we will study it later. Study it later means we will use just this condition, boundary condition, during solving problem, right? Okay. So I'm just taking an example. These examples are given in the books and the literature from the research. Okay. So yeah. Okay. So these two, first one is fluid is flowing and this one is turbulent flow. Okay. Turbulent flow and this one is laminar flow. Okay. And what this two line denotes is, velocity profile. Okay. Velocity profile. So you can see that this is the wall. Okay. So one fluid is flowing above this wall and that is turbulent flow. Okay. So in that case, in turbulent flow as well, the velocity here we can see that, this direction, we will see the velocity. Okay. These are the velocity, right? So in this condition as well, the velocity at the wall is 0, and in case of laminar as well, the velocity at the wall is 0. After the wall, the velocity profile can differ for turbulent flow and laminar flow. In laminar flow, it's making seems like very smooth, right? And that's the definition of the laminar actually. That laminar flow is very smooth and in very, what is it, in very uniform and periodic manner, whereas turbulent is like a very random kind of thing. Okay. So we can see that random things are here, and in case of laminar it's very smooth, right? So the after that interface point, the behavior of the both the fluids can be differ, but at the interface point the velocity of the both the liquid is 0 and the behavior of the fluid is same. Okay. So this two condition, two boundary condition will be applied to both turbulent and laminar flow. Okay. It doesn't matter to type of flow. Okay. So in both cases there is clearly no slip at the wall, where the water takes on the 0 velocity at the fixed plate, right? The velocity profile is made visible by a discharge of a line of hydrogen bubbles from the wires, which was done in any experiment. Okay. Now we will see that this condition, we have studied this all these things excluding these rarefied gases, very thin gases, right? Now we will study the things for rarefied gases only. Okay. Rarefied means the gases which are very thin, the density is very low. Okay. So for these cases we will not expecting to fluid that they will reach to the equilibrium. Okay. That means the velocity of the fluid and the velocity of the solid may not be equal at the interface for the case of rarefied gases. Okay. So in that case, for example, this one the interface and the fluid is flowing, these gases are flowing and the rarefied gases. So in that case we can't say that that no slip condition will follow. That means the velocity of wall, let's suppose velocity of wall is 0. This pipe is there and the pipe is not moving. So in that case the velocity of the wall is 0 and the fluid is flowing, right? So in that case we can't say that the velocity of the fluid is equal to velocity of the wall and that should be equal to 0 at the interface. No, we can't say that. Okay. So what we used to do is, for mathematical non-difficulty. I mean, we have to avoid the difficulties in mathematics. Okay, so we build partially released the relax the no sleep condition. Okay, and the flow is allowed to sleep past the surface but not to permeate through the surface. Okay, that means that means this tangential velocity of the fluid, okay, is not equal to velocity of the wall. Okay, okay, but this I mean this normal velocity, okay, this one is tangential velocity, right, according which this one is normal velocity. So this normal velocity should be equal to velocity of the wall. Okay, and that should be equal to 0 because the wall is not moving, right? So we can say that we just have relaxed the mathematical difficulties here to use this condition, and we will allow the fluid to having some velocity irrespective of whether the wall is moving or not in case of rarefied gases, right? So we call it as sleep condition. I mean, this is sleep condition, this is not a no sleep. In case of no sleep, this velocity of the fluid should be equal to velocity of wall, or for this case, the I mean cylindrical pipe is at rest, so that we just simply made it 0. If this one is for all these gases, I mean the fluid, I mean especially for the viscous fluid, we can just make it simply 0. But in this case, since I told you that this one is rarefied gases, and most of the time we take rarefied gases as ideal gas. Okay, so whenever a ideal gas is given, so we can use these conditions. I mean this sleep condition. Okay, I'm just read it here. I mean here I've written sleep flow in gases. We will discuss it here later. How we will find this sleep velocity, I mean this velocity, right? We just find this normal velocity according to the wall, right? In this case, or the most of the cases, this wall are at 0 velocity, we will simply put it as a 0. Okay, or if the wall velocity is given, we can find it. Okay, as we have seen, for high viscosity Newtonian fluids, the linear velocity assumption and the no slip conditions can yield some sophisticated approximate analysis for 2D and 3D dimensions viscous fluids as well. Okay, so these conditions make easy to, I mean, develop equations and analyze it easily in 3D condition as well. Okay, but in case of rarefied gases, it seems difficult. Okay, now we have seen that in the here rarefied gas follows sleep condition. Sleep condition, because they are not following that no sleep condition that we have discussed it earlier, that the whole velocity of the fluid will become equal to the velocity of the wall. Okay, so this is only valid only to for normal velocity. Okay, but for tangential velocity, we don't know the velocity of the fluid at the interface as well. Okay, so for during solving any problems in fluid, we need actually a bounding condition. Okay, and without bounding condition we can't solve any equation. Okay, but in this case I've seen that the normal velocity is known, whereas the tangential velocity at the interface is not known. Okay, so that means the bounding condition is not known to us. So for solving any problem, it seems tricky. Okay, right? So how we will deal with that? Okay, so however, this pre-sleep boundary condition, I mean this one, that the normal velocity should be equal to 0 and tangential is we have to find out. So this is an realistic mathematical artifice to, I mean, enable in viscous flow solutions. However, actual realistic wall sleep occurs in rarefied gases where there are two fluid molecules to establish momentum equilibrium with the wall. Okay, so in that case we will use sleep flow. Okay, that we have discussed. So in 1879, the physicist James Clerk Maxwell used a kinetic theory of gases to predict the sleep velocity at the wall. I mean this tangential velocity, and that can be written as U wall. Okay, this is the sleep velocity at the wall is equal to, I mean, L into du dy. Okay, and wall. Okay, so this is the equation that he has given, and remember that this one is given for real ideal gas. Okay, and most of the time for rarefied gases, I mean rarefied gases means very low pressure. So at low pressure and high temperature condition, we assume this airy gases to be ideal gases. So I mean very close to rarefied gases, or the rarefied gases are very close to ideal gas. Okay, so we just simply take that any rarefied gas as ideal gas equation, so we can use this condition. Okay, so we can use that this one is the tangential velocity. Okay, so for that case we know that bounding condition. Okay, so now we can solve any problem, right? Because Vn will be known and Vt as well known from this condition. Okay, so now what's the term that here in the equation? L is the mean free path. Okay, so I mean I have explained you what's the mean free path. So it's just the path traveled by any molecules or the particles between two consecutive collision is known as mean free path. Okay, okay. So mean free path of the gases. Okay, and u is velocity along wall. Velocity along wall, I mean the tangential velocity, this one along the wall. Okay, okay. And x is also along the wall and along wall. Okay, that means y is along this I mean in this direction. Okay, y is just perpendicular to the wall. Okay, okay. And now we see if L is very small compared to the lateral scale capital L of the flow, the Knudsen number. Okay, 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 okay. Okay, so I'm just not tell you the statement. I will just explain you to here. Let's suppose any pipe is there, right? And the pipe length is too long. We will say it L. Okay, and if this L means mean free path. So if L is very small as compared to this lateral scale, I mean if L is very small as compared to this, one number is defined here. Knudsen number, that is L by L. Okay, small l by capital L. So in this case Knudsen number become very less, right? Okay, so in this case the slip velocity is almost equal to 0. That means we can use the no slip condition. No slip condition will be true. Okay, okay. So I mean this characteristic length, or sorry, mean free path length is very small as compared to, okay, I will write it Knudsen number, KNUDACN. Okay, Knudsen number. So whenever this L, I mean a small L, mean free path is very less than that the lateral length, the total length of that the dimension of the part pipe or anything. When it's very large, then we can use the no slip condition will be valid ever. Okay, okay. So I hope you have all understood this no slip condition and the no slip condition and the no temperature jump condition. I mean these things are very important. You will be going to use it ever and ever in the time. Okay, for solving the fluid problems. Okay, so I hope you all understand this lecture. So till then, keep learning and goodbye.